You guys have learned about a fundamental theorem of arithmetic. You've learned about a fundamental theorem of algebra. Do you remember what either of those two things are?
No.
Okay, fundamental theorem of arithmetic. You don't see this a lot, and we don't ever actually call it that. If you had me your freshman year, we actually kind of referred to it a little bit. But the fundamental theorem of arithmetic says that every integer, or we'll say every integer greater than 1 can be expressed as a unique product of primes. Oops. So this is just the factoring one, that every number has a unique prime factorization. And as arithmetic, it kind of refers to really what multiplication is all about, and how every number's factorization is unique, and so then every polynomial's factorization can be unique. And the uniqueness of that is the important part of that. Like, you're not going to have more than one number become 2 times 3 cubed. That's a single number. If you want to change the number, you change its prime factorization. The fundamental theorem of algebra is one that I kind of extend beyond what the actual fundamental theorem says. It's that a polynomial of degree n has n roots. So that should make sense. If we kind of extend it to complex numbers, we can qualify that. This is one of the reasons that complex numbers was so essential to algebra. Otherwise, it's not complete. And you describe that. One of the neat things to do is to visualize, and it's hard to do this, and I'm looking still for a computer program that does this. If you guys find one, I'd be really grateful. That does three-dimensional graphing of a function where one plane is real numbers and the other plane is pure imaginary numbers, and the 3 dimensions are the complex numbers. Because then you actually truly can visualize the complex roots of any function. But that's only true if you're taking, if I take y equals x squared and I graph it in complex numbers on a complex plane, it takes on a 3-dimensional shape, and you can see the roots of that in 3 dimensions. So it's a neat facet of it, but it's one that it's really, really difficult to find and create. So this one is the fundamental theorem of calculus. And we have 2 parts to this. Today is part 1. So part 1 and part 2 are different parts. They're kind of completely different from each other. They might as well be 2 different things. But the fundamental theorem of calculus part 1 says that if f, function f, is continuous on the closed interval a to b, a condition that is very, very much required, and one of the emphases next year for you guys is going to be on these conditions for these theorems. It's something that's increasingly important in the AP exam. They want to see that you have an understanding of conditions. Things like when you had the mean value theorem, things like when you had Rolle's theorem, that you know what the conditions of that are. If f is continuous on the closed interval a to b, and capital F is an antiderivative on that same interval, then the integral from a to b of f of x dx is equal to f of b minus f of a, capital F of b minus a capital F of a. And that has huge and far-reaching implications on how we evaluate definite integrals. One of the proofs of this, and this is going to be a little mini proof for you, has to do with taking a region like this, where I have a and b as my endpoints. And if I call this region capital F, what I'm going to do is separate this into many, many, many sub-intervals, where this is x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and so on. And I'm going to call this a now x sub 0, whereas b is going to be an x sub n for just kind of n intervals. And I also know that since they're all x values, x sub 0 is less than x sub 1, is less than x sub 2, is less than x sub n minus 1, less than x sub n. They all kind of rank in order. Well, the proof of this is that f of b minus f of a is really f of x sub n minus f of x sub 0, since I kind of relabeled those. And what that means, if I algebraically work that out, is this is actually f sub x sub n minus f sub x sub n minus 1, the difference there, plus the next difference, f of x sub n minus 1 minus f of x sub n minus 2, plus all the little differences you can do right down to f of x1 minus f of x0. Do you see why algebraically that would actually be the same thing as the step right above? The cancellations that would come into play, these would cancel, the next ones would cancel. The only thing remaining would be your endpoints. So it's like you're adding up all the differences, all the infinite number of differences. And when you add up an infinite number of things, that's the kind of very definition of what happens in calculus. This is the sum of all of the f of x sub i's minus f of x sub I minus 1's. It's the sum of all of those from I equals 1 all the way up to n. And that is capital F of B minus F of A. Now, by the mean value theorem, in each interval, or in each subinterval, I should say, so a subinterval is each one of those little things, each one of those little pieces. In each subinterval, there is a c sub I. So what I'm saying is there is some value in there, some c sub I or x value, such that the derivative at that c sub I value is equal to the slope at the endpoints. So I'm going to hold on this for a second and just kind of visualize what this is saying. There's a lot of variables going on here, and that's what's difficult to understand some of these proofs. You don't ever have to recreate the proof, but let's just say that this right here is one of my intervals. Here's an x sub I minus 1 and x sub I. So that's just one of those intervals up there. There are like lots and lots and lots and lots of little subintervals, but this is one of them. And somewhere in there, there is a c value so that the instantaneous rate of change is equal to the average rate of change. That was the mean value theorem itself. And we've already established that this graph is continuous, so I don't need to worry about that as a condition. That means that at that place, that means instantaneous right here is equal to average. With me so far on that? The derivative is the instantaneous rate of change, and the average rate of change is the slope that we find. Well, f prime, capital F prime of c sub I, what's that really? What was capital F? The antiderivative. So what would this be really? Lowercase f of c sub I. And that's the same thing here. And so if I know those are the same thing, well, I'm going to kind of rewrite this a little bit to where, all right, so that's equal to lowercase of this. Let me kind of swing this right back around, way back up here. If I start taking like kind of the summation of all of these, and so I'm going to kind of swing back up here and just do a sum on all of these things. If I do the sum from I equals 1 to n of this numerator, f of x sub I minus f of x sub I minus 1, over, let's call this denominator delta xi. It's just kind of easier to use a delta notation. Well, that's right there. If I kind of then just treat this as, all right, I'm dividing by a delta xi, let's introduce a kind of like a times delta xi right here. So I'm going to do that on the left side. And if I do that sort of on the right side, because I'm adding up all these little infinitely many things, basically I can say that this is the same as f of b minus f of a. Adding up the infinitely many things, dividing by the delta xi's. If I were to kind of cancel those, I would just get the summation that we had before. So this is a little convoluted way, and I'm going to kind of just go over this one more time here. We have that this whole thing right here is equal to f of ci. I have that this whole thing here, if I cancel those delta xi's out, is really just the f of b minus f of a, because we kind of established that already. So knowing that, this is where the calculus comes into play. Let's do a substitution. This is just lowercase f of x sub I. I know that because of the equality we just kind of hit up above. This right here is times xi, and then this is the calculus. C sub I? At this point, we're just calling it f of x sub I. I'm just kind of saying this is the same as really what the derivative is. The delta xi's, the delta is like a macro thing. It's like a huge, huge difference. What's the micro version of that? So if delta x is like a macro, they're like very visible differences. What's the micro version? What's the infinitely small version of delta x?
f of x plus h minus f.
Because that's the definition of the derivative. I'm talking about the infinitesimally small d. You guys would say it. That's the dx. Delta x and h are kind of the same. Well, almost the same thing in that case. But no, the dx is what I'm going for. Like the infinitely small width. So this becomes dx. A summation in calculus, that's where you do an integration, where you're adding up an infinitely small amount. That's what an integration is. This is the integration of my limits of f of x. And we still have the f of b minus f of a. So bottom lining it, and this is the proof of it, and you can kind of put a little QED at the end, which means quod erat demonstratum, or thus it is shown. Means you've ended your proof. What we're showing in this is that the difference in the function values of the antiderivative is going to be the same as the accumulated infinitely small areas that you have here. And that's a very, very neat and viable outcome. This now means that if you can find an antiderivative, you can evaluate a definite integral. And definite integrals, very much for a lot of you, are going to be preferred to indefinite ones because you come up with a numerical value. You also can calculate definite integrals in your calculator. And you will need to do that on the AP exam several times over, especially, obviously, in the calculator section. They give you functions that you can't evaluate otherwise, or would be, I should say, too burdensome to do, or take too much time. So the integral from 2 to 3 of x cubed minus 1 dx is something that we have not been able to do with visual methods. You could, no, you couldn't. As I say, you could do the integral from negative 3 to 3 of x cubed dx, but that's because you have an understanding of what symmetry does. What would that be? It would be what?
0.
0. Yeah, this would be 0. Because the graph would be like that. So it's symmetrical left and right. So you have area below and above matching. But anything off-shifted like that, you're not going to be able to do. So the first thing you do is take the antiderivative of this and the antiderivative of the 1, x. Once you take, you actually don't need that anymore, because, and you can kind of reason through, if you're going to add c to both the things that you're subtracting, the c's are going to cancel off. So you don't need the c, but we're going to do a parentheses here and evaluate this from 2 to 3. This is the notation that you're going to use when you evaluate. And all that means is you're going to substitute 3 in, 3 to the 4th over 4 minus 3. and then subtract what you get when you substitute 2 in. 2 to the 4th over 4 minus 2. So simplify that down, 81 fourths. You have minus 3 plus 2. I kind of look for my constants and group those together. And then let's subtract 16 fourths, which is 4. And then you get 81 fourths minus 3, 81 fourths minus... Yeah, hang on, I'm checking because I'm differing on what I put here. Oh, this should be a negative 1. Yeah, that's a negative 1. So minus 5, so minus 20, you get 61 fourths. How did I get negative? Negative 1 because negative 3 plus 2. I'm trusting at this point we can kind of look ahead beyond the distributive property just a little bit. So you're going to do a lot of subtracting groups. Like a lot of times we have a group minus a group. So it's going to be to your advantage to kind of group together your constants and keep these going. Okay, number 2. I want to throw this down just to kind of give you like one final reminder, especially heading into tomorrow, about ones that you can't do. So this is an integral that you still do not know how to do by hand. You don't need to. That's a semicircle. It's a semicircle of radius 5, and you're doing just kind of a quarter circle here. So that is a geometric formula to get that integral. Even though it's a definite integral, you're not going to use a calculus means to do it. So it's 1/4 pi r squared, which is 25 pi over 4. But let's actually evaluate something that I hope you've been somewhat curious about. The integral from sine of 0 to pi over 2 of sine x dx. This is the integral of what we call an eta. So you've heard me talk about pi, and you've heard me talk about tau. Eta is the 4th. So a single eta is like a single quadrant. And on a sine graph, something you guys are expected to know how to graph consistently. Sine starts here, ends here. Halfway through, you kind of pass through the baseline again, and it goes like this. This is a single cycle of sine. Yeah, it's 2 pi. So what I'm asking you guys to essentially do, I always do it when I graph each eta. That looks better. What I'm asking you to actually find is like this area right here, which would be this single little bit there. So the integral from 0 to pi over 2 is going to be one of those. Integral from 0 to pi would be double that, and integral from 0 to 2 pi would be 0. I mean, this just gives you that like understanding of what's the area of one of those little pieces there. So we're going to do this integration. Integral of sine theta is negative cosine theta, evaluated from 0 to pi over 2. So then when you substitute, you get negative cosine of pi over 2 minus negative cosine of 0.
0 plus 1.
You get 1.
Wait, why can you do it? Why'd you put theta to 0?
Oh, that should be a 0. So what would the integral from 0 to pi be? 2. 0 to 3 pi over 2? 1 again, because we cancel out, making sense. The integral from pi over 2 to pi
1.
of sine x dx.
1.
Would it be negative 1?
Negative 1. Oh, sorry, no, pi over 2 to pi would be 1. You're right, Liv. Sorry, pi to 3 pi over 2 would be, that'd be negative 1. Okay. Any questions so far before I kind of move on to a few other examples? Okay, number 4. Integral from 1 to 9 of 5 root x dx. When you have a constant like this, I would pull the constant out, rewrite it as a x to the 1/2 so you don't confuse yourself when you raise. It's kind of easier to see it there. Raising to the 3, now x to the 3/2, but you'd be multiplying by 2/3. So 5 times 2/3, which can still be factored out. And then you just have x to the 3/2. That's evaluated from 1 to 9, which means it is 10/3 times 9 to the 3/2 minus 1 to the 3/2, or 2/63. So how can we make this a little bit more challenging? Because you're not going to be given just a straight up definite integral at some point. This is one of those like basic skills that's going to be part of something bigger. But a few things we can do is do something like this, where I give you an absolute value. Go ahead and graph this just to get an idea of what's happening. Yeah. Apologize for the pauses. I'm awkwardly trying to stare down someone who's playing on his, or still on his phone, thinking that that's like an okay thing. Can we put it in the backpack? And by we, we mean you, because it's not like a we thing. It's a you thing. That is the patronizing way. So, graphing this, the idea behind an absolute value is that you have to split it. You can't do an integral about an absolute value. You're going to have to split it into a piecewise. If you remember, I hate to keep pointing to freshman year, but we did this a lot your freshman year. We took an absolute value function and split it into a piecewise. I specifically remember where this is, where this happens, and all that, because we did last semester. But we asked you to graph and write, this is actually the same thing as y equals, it'd be a positive 2x minus 3 whenever x is greater than or equal to, what's the value?
2/3, or
3/2. And then negative whenever x is less than 3/2. You don't have to write that for me, but I do want you to kind of understand where that split happens and what's going to be going on here. What's really happening is you're going to do an integral from 0 to 3/2 of the opposite of that, negative 2x plus 3 dx. And you're going to add that to an integral from 3/2 to 3 of the positive version. Do you see why that's going to get it? So, on this one, to make life easier for yourself for this first integral, I would factor the negative out and then do the integration on both. The integration of both is going to be the same. You're going to have an x squared minus 3x, 0 to 3 over 2, plus, and then this is going to be x squared minus 3x from 3/2 to 3. So you get negative. Watch the negative outside. I'm going to do like a larger parentheses. 9/4 minus 9/2 minus, this is just going to be 0 minus 0, plus, then you have 9 minus 9, then minus 9/4 minus 9/2. You see this a lot where you get certain amounts of symmetry happening, but just kind of track it through. Sorry, my negative should be, yeah, that's right. So this is 9/4 minus 9/2. That is going to be a positive 9/4 plus negative 9/4 plus 9/2. You have another 9/4. 9/4 plus 9/4 is 9/2. Okay. Let's go to the next example. Wow, I had a lot less time last year. Okay, let's do this one. So this is actually pointing to something that will be helpful for tomorrow as well. We talked about this yesterday in class, and we're kind of hitting this up again. This second part right here. I would really expect you to look at that and know what the value of this would be right away. 56. Visually, that is a rectangle with a width of 8 and a height of 7. That is different than taking this and just adding 7. And that should be very, very evident. This part, though, when I want to integrate this, there are two ways to do that integral. One's easy, one's hard. The easy way is not the u. That's not the hard way either. That's kind of medium. That's what I would expect you to do. If I gave this problem right now to my seniors in BC, 100% of them would do u is equal to x minus 4. But that's not the easiest way. The easiest way is to graph it in your head right now. It's a right shift of x cubed. Yes.
God, I'm a genius.
Oh, you are something. This is
Oh, it's because 4 is in the middle of 0.
this is y is equal to x cubed. At x equals 4, it's this, and I'm going symmetrically about 0 to 8 is going to be about that. Do you see it now? So this would be 0 plus 56 or 56. I've seen it a couple of times on practice AP exams where this question is thrown in there, and it's purely to see can you get it quickly. Like, even if you don't, it's like those little precious seconds you lose just doing it the manual way. You could have used on something else. So it does come down to, like, they want to see, can you just recognize the symmetry? It's not difficult to do. I mean, I'm going to do an example with the u substitution that's going to show this. So let's go integral from 1 to 5 of, let's do 2x radical x squared plus 1 dx. Okay. Usually I wait till day 2 to show this u substitution. I'm going to show a couple now just to kind of prep for the coming days, knowing that my people who are gone are going to be watching this too.
Hello?
I hope. I hope Alex is. He's the only one that didn't take the test.
That they have to tell you before they watch.
I should, but then they just tell each other what that thing is.
But
Alex won't watch it.
Okay. If you're hearing this, the next words you have to say to me are Cookie Monster.
If you're reading this, it's too late. No, do
but don't
No,
tell each other.
Cookie Monster. Better that than the intersection of two circles. So,
Analyst.
yeah. Hi.
Can you please have Zach Angle?
Sure. Okay, so what are we going to let u equal?
You. X squared plus 1.
X squared plus 1. Are you leaving? Du.
2x. Dx.
Whatever.
Oh, take. Sorry.
Let's place bets.
Hang on. Do you remember when I said that when we do this this conversion into u's, that everything has to be in terms of u's?
Yeah.
So when I say everything must be in terms of u's, that also means things that you might not be thinking of. So it's the x here, the x here, the x here, but there are also two other values that are x values, the limits. This 1 and this 5 are limits in terms of x. You have two options on this. You can either convert everything to u's to do the integration, then go back to x's. That's not my preferred option. The other option is to recognize that this right here actually generated a function of u in terms of x, meaning that u of x is equal to x squared plus 1. So then these limits can actually change now. If I take 1 and plug it into the function, I get, if I take 5 and plug it in, you get 26. If you do the u substitution, the two x's are going to cancel, and you're going to get root u du. You will never have to go back to x's now. You're doing an integration with a simpler operation entirely in terms of u, and this value should be exactly the same as this value.
So it's just square root of 2, square root of 26 minus square root of 2.
Then you have to integrate now. You have to do the integration. So this is u to the 3 halves times 2/3. Guys, please. No plus c here because we are doing an indefinite integral. And don't put the 2/3 in that in evaluating. I would pull the 2/3 out and just kind of leave it like this. Now, hang on. Before I move on, though, I want to see, like, I do want to ask, does anyone have questions about how I went from here to here? Like, speak now or kind of forever hold. Leo.
So, you don't have to do plus c because you know the bounds?
If we're doing a definite integral, we don't have to. And here's part of the reason why. When I add c and then subtract off adding c, you're going to have a c minus c.
Oh, because it was,
Is that a negative sign right after 2/3?
No, that's a dot.
Okay.
It's a failed dot, but it's a dot. In any case, I get 2/3, 26 to the 3/2 plus, or not plus, minus 2 to the 3/2. You would probably leave it like that and then approximate it with a calculator at some point. It's not worth kind of going through and trying to decide, do we want simplified radical form or do we want not. 2 root 2, 26 root 26 versus 26 to the 3/2. It's kind of, at this point, it's all the same. Like, you don't need to say 26 to the, or 2 to the 3/2 is 2 root 2. You don't need to do that anymore. Leo, I'm going to kind of hit up your question here a little bit more specifically. So let's say that my integral was u to the 3/2 plus c, which isn't wrong to put. But do you see why in the subtraction the c's are going to go away? So for definite integrals, just by convention, you will never see them written in any of the work you ever see with a c. That's a lot of c's. Okay, we're done. You guys can start or study or do whatever. Oh, not whatever. Max, you have very specific things you should do.
What? What are the specific things?
Anything not involving phone and anything involving academia.
Then consider it done.